Welcome, everyone. It is a pleasure to have you here for our session on the complete Codebase lifecycle, from first commit to final archive. Today, we will undertake a strategic walkthrough of application governance, focusing on the powerful integration of Azure DevOps, Azure Container Registry, and Azure Kubernetes Service. We will explore the entire journey of a codebase, from that very first line of code and initial commit, through containerization and deployment, all the way to its eventual archival. Our goal is to provide you with a comprehensive framework for maintaining security, compliance, and efficiency at every stage of the development pipeline. Let's begin. The life cycle of a modern application follows a four-phase journey from its initial inception to its final sunset. This process begins with inception and integration, where the codebase is first created and integrated into a functional framework. From there, we transition to deployment and operation, the phase in which the application is launched into live environments to begin serving its purpose. The third phase, maintenance and governance, involves the ongoing efforts required to keep the application secure, compliant, and efficiently managed throughout its active lifespan. Finally, the journey concludes with archiving and decommissioning. This final stage focuses on the secure and compliant retirement of the application, ensuring that all data is properly archived and systems are decommissioned according to industry standards. Phase 1 focuses on inception and integration, representing the crucial first step in the life cycle of a software product. The core objective during this phase is to transform raw code into a secure, versioned artifact. By establishing rigorous versioning and security protocols at the outset, we ensure that the codebase is well managed and protected before it progresses to deployment and operation, maintenance and governance, and eventually archiving and decommissioning. This foundational work is essential for maintaining integrity and traceability throughout the entire development process. The continuous integration loop begins with a dedicated focus on code quality and security. The process is initiated within an Azure repo when a commit or a pull request merge to the main branch is detected by the Azure Pipelines.yaml file. This event automatically triggers the CI stage of the pipeline. Once active, the pipeline agent executes two primary workflows in parallel. First, it performs linting and unit tests, utilizing tools such as PyTest or .NET Test to ensure the code meets established quality standards and functional requirements. Simultaneously, a security scan is performed. This involves static application security testing, or SAST, where specialized tools like SonarQube or Microsoft Defender for DevOps analyze the source code for potential vulnerabilities. By shifting these checks to the beginning of the cycle, we ensure that security and quality are built into the software from the very first step. Packaging code as an immutable and traceable container image is a fundamental step in our CI/CD process. This begins with the Docker @to task, which builds the container image directly from the project's Docker file. Following a successful build, the pipeline utilizes a service connection for secure authentication to push the tagged image to the Azure Container Registry. By doing so, we create an immutable artifact that serves as a single source of truth for our deployment. To maintain high standards of traceability, we follow a strict tagging strategy. Images are tagged with unique identifiers, like the build.buildID or the git commit SHA. We must avoid using the latest tag in production environments, as unique tags are essential for identifying the precise version of the code in use and enabling reliable rollbacks if necessary. We are now moving into Phase 2, which focuses on deployment and operation. At this stage, our primary objective is to transition the secure artifact from the registry into a live Kubernetes environment. As you can see in the process diagram, this phase follows inception and build, serving as the bridge to active production use. Our focus here is on ensuring that the artifacts we have secured are deployed efficiently and operated reliably within our Kubernetes infrastructure. The continuous delivery process is triggered by a successful push to the Azure Container Registry or the completion of the CI stage. The first critical step in this workflow is preparing the Kubernetes manifests for the specific deployment target. In the manifest preparation phase, the CD pipeline stages and updates the necessary Kubernetes manifest files or Helm charts. Utilizing tools like Helm or Customize allows for a more streamlined and templated approach to managing infrastructure as code. Next, we address dynamic configuration. At this stage, environment-specific variables, such as the new image tag, for example, image.myapp.v1.0.5, are injected directly into the manifests. This is typically accomplished using a replace tokens task within the pipeline or via Helm values overrides to ensure each environment receives the correct configuration settings. Executing a zero downtime deployment to Azure Kubernetes service involves a coordinated workflow between your deployment pipeline and the cluster. First, a secure service connection allows the CI/CD pipeline to communicate with AKS. The pipeline then executes tasks such as Kubernetes manifest or Helm deploy, which trigger the cluster to update its state using standard commands like kubectl apply or Helm upgrade. To retrieve the updated application, AKS authenticates with the Azure Container Registry using either a managed identity or a pull secret to pull the latest container images. Once the images are ready, Kubernetes manages the deployment through a rolling update strategy. This process gracefully replaces old pods with new ones one at a time, ensuring that the service remains available throughout the transition and resulting in zero downtime for end users. Phase 3 focuses on maintenance and governance, a critical period dedicated to ensuring the security, efficiency, and stability of the active application. Having successfully moved through the inception and deployment stages, our efforts now shift toward long-term operational excellence. This phase involves continuous monitoring and strategic oversight to maintain peak performance throughout the application's active lifecycle, bridging the gap between its initial launch and its eventual archive. To maintain a healthy and secure system, we must prioritize active lifecycle management across our infrastructure. For the Azure Container Registry, we implement automated image retention policies to delete old or untagged manifests. By limiting our storage to a set number of versions, for example, the last 10, we can effectively manage costs and eliminate repository bloat. Security is handled through continuous vulnerability scanning. By enabling Microsoft Defender for containers, we ensure that all images in the registry are checked against newly discovered CVEs, alerting us to potential risks immediately. For the Azure Kubernetes service, we address configuration drift by implementing GitOps with tools like Flux or Argo CD. This ensures that the cluster's live state remains synchronized with the configuration defined in our Git repository, allowing the system to automatically detect and correct unauthorized manual changes. Phase 4 represents the final stage of the application lifecycle, archiving and decommissioning. This critical phase focuses on securely sunsetting the application to terminate ongoing billing and ensure that all necessary compliance data is properly retained for the long term. As shown in the progression from inception through deployment and governance, this concluding step is vital for maintaining efficient resource management and meeting regulatory obligations. By executing a formal decommissioning process, we ensure the application's retirement is handled with the same level of security and oversight as its initial launch. Decommissioning active infrastructure and pipelines requires a methodical approach to ensure both cost efficiency and data integrity. Beginning with AKS resources, we start by deleting the specific Kubernetes namespace associated with the application. If the cluster is dedicated to this workload, the entire AKS cluster resource should be deleted to stop all ongoing compute charges. Regarding ACR images, the priority is to identify and lock any golden release images to prevent their accidental deletion. Following this, all remaining development, feature, and test images should be purged to streamline storage. For pipelines, we must explicitly set them to a disabled state to prevent any unintended triggers. It is also necessary to configure specific retention policies to maintain build and release logs in alignment with compliance requirements. A vital component of this process is critical data preservation. Before any AKS resources are deleted, ensure that data stored in persistent volume claims is backed up to Azure Blob Storage if it must be retained for legal or business purposes. This ensures that valuable information remains accessible even after the primary infrastructure has been removed. To begin the archiving process, we must first make the repository read-only. Within the Azure DevOps project settings, we modify the repository permissions to set Contribute to Deny for all groups, which effectively locks the codebase and prevents any further modifications. Next, we establish a definitive reference point by creating a final, descriptive Git tag on the main branch. Using a convention such as archived, followed by the current date, clearly marks the exact state of the code at the time of sunset, making it easily identifiable for future reference. Finally, as an optional step for ultimate long-term retention, the codebase can be migrated to cold storage. This involves cloning the repository, compressing it into a zip file, and storing that archive in the archive tier of Azure Blob Storage. This approach ensures the data is preserved at the lowest possible cost while remaining available if retrieval is ever required. The Lifecycle Governance Checklist provides a summary of the critical controls necessary to manage a software project across its entire lifespan. In the continuous integration phase, we focus on whether code is being built, tested, scanned, and pushed to the Azure Container Registry automatically to maintain high quality and security standards. Transitioning to continuous deployment, the key control is ensuring that every successful build triggers a deployment that correctly updates the relevant pods in Azure Kubernetes service. For ongoing maintenance, it is essential to have an active ACR retention policy and to ensure that container images are consistently scanned for vulnerabilities. Finally, during the archive stage, we must confirm that the final pipeline is disabled and the repository is set to a read-only state to prevent any further modifications.